Voronoi diagram? Pah! Get out of here. Delaunay triangulation? Pah! You're not my dad. Alpha complex? Pah! Pah!
The goal of this tutorial is actually quite simple. We are going to take a point cloud and try to extract the surface that makes it up.
And I'm going to be honest with you, this is a hard tutorial. We're going to be doing the two-dimensional case because 3D is just too much. For the project files and the 3D version, I have that over at my website, or I've made this like 3D solver that I put in Genie, which is my add-on of add-ons.
This video is sponsored by Brilliant. More about that later.
Really, our problem is in 3 dimensions, but we're going to start with 2 dimensions because it generalizes and is less work for me and for you. I want you to imagine we have a bunch of points. These points are vertices in what should be a mesh. The issue is, how do we triangulate it? How do we extract a surface from it? Seems pretty easy. You're just like, oh, if points are next to each other, connect them with triangles. And there you go. I've extracted a surface. Fine. But there is a lot of ambiguity. For example, this point right here and this point right here, should they be connected? It's not clear because maybe my shape was this kind of big thing, or maybe it was the skinny thing. Imagine we just have like 4 points. How big of a deal could that be? So I've made my triangulation with 4 points. It's perfectly valid. But even in this simple case, we could have flipped an edge, right? So instead of doing this, here's another valid triangulation. And in fact, we'd say that this one is better in some sense. If we can understand why this triangulation is better than this one, we can extend the principle. The reason we don't like this one is there's very skinny triangles. This kind of leads to a mesh that doesn't look good. Whereas if I kind of do this dividing line over here, you can see these triangles are closer to equilateral. How do we make our angles, our triangles, not skinny? There is a way to formalize this. I want you to see that we have 3 points here, and there is kind of like a special circle that touches all 3 of these points. It's called a circumcircle. It has a name. Some dude went out there, he's like, what should it be called? Circumcircle. And what you're going to notice is that this circumcircle does not include this point. They're totally separate. They're far away from each other. Also true over here. So here's a circumcircle, and this is separate. But what if we add this triangulation over here? Well, then these 3 points make a giant circumcircle, and this circumcircle includes this other point. In other words, we don't like it, and it happens in both cases. So it turns out this problem of preventing skinny triangles is exactly the same as picking a triangulation where no point lies in the circumcircle of another. We can do a triangulation iteratively with this rule. How do I know to not make perhaps this triangle? Well, because it has a giant circumcircle that might include a point over here. So I'm going to start off with the plane. I'm going to merge these to be a single point and just start duplicating things. So this is going to be our 2D kind of photo scan situation. Well, here is an algorithm for getting this. It's called a Delaunay triangulation. I'm going to start off with a big triangle. It just has to contain all of these points. And then I'm going to start off with a single point. So let's say we start off with this one. Because this new point is inside the circumcircle of this giant triangle, we know that it is a problem. It's not valid. So I'm just going to create new triangles here. And now it can't be in the circumcircle because it is touching all of these triangles. Now I'm going to move on to this point over here. Is it inside the circumcircle of any triangle? Well, it is in this giant triangle over here. And in fact, it is possible for it to be in multiple circumcircles. So this one, the big triangle, whatever. If it's an issue, all we do is we then triangulate it. And this is something that we do iteratively. So let's try to make this a bit cleaner. I have my big triangle. This point is offending. It's offending me. It's offending you. So we create a new triangulation. And now this is called Delaunay. It doesn't have any issues. And we move on to the next point. So let's say we're doing this one. It is inside this circumcircle of this triangle. So we take it and we break it up. This point is in fact in 2 circumcircles. So this triangle over here, it makes a giant circumcircle that this is inside, but also this triangle over here, it creates a giant circumcircle that this is inside. So now it has 2 kind of triangle offenders. They're having a party. And we need to fix this. Instead of just kind of like triangulating this one and kind of doing the same with the other triangle, we got to make sure we do this in a way that is still Delaunay. I'm going to get rid of this edge that was connecting these 2 triangles. So now it makes a polygon. And then we triangulate as normal, but this time we make a triangle fan that has 4 lines, which creates many more triangles. And now let's say we have this point over here. You're starting to get the idea. It is inside this bigger triangle, of course, which has this giant circumcircle, but also this triangle over here. It has a big circumcircle that the point is inside. So we just get rid of this connecting edge between them and we create a triangle fan. This algorithm has a name and I'm sure the people want credit. So here you go. And then in 3 dimensions, instead of doing circumcircles, would you believe it? We do circumspheres, but whatever, that's for later. I need to start off by making a big triangle that contains all of these. How can I ensure that's the case? Well, I'm going to make a bounding box. So here you can see they're all perfectly contained and I'm going to get the diameter of this box. In other words, kind of how big is this diagonal over here? We take the maximum and the minimum and we get the distance that is between them. And we can use this to make sure we can make a triangle that's big enough. So to make a triangle, I'm just going to start off with a mesh circle, bring down the vertices until we have a triangle. Do you see what I see here? I don't know if you do. Okay, so this is going to be our triangle that can have a certain radius. What should that radius be? Well, I can make it the diameter and then be sure that this is big enough. Yeah, it's a bit overkill, but it perfectly contains our points and therefore is good enough. Now, the next step is we got to pick a point, like let's say it's this one, and add it, and then see if it has an issue, and if so, triangulate. Separate geometry such that we only keep the one of index equal to 0, or whatever you want it to be, and now we've separated out this point and the rest of them. You're going to see that it, of course, is in the circumcircle of the big triangle, so we have to break it up. What's the easiest way to break up a triangle? It's to insert pressure and familial pressure and all of this. But in this case, what we're going to do is I'm going to extrude the mesh, making sure to extrude edges. This way I can make sure that I'm creating new faces like this. If I kind of scale this to a small enough number, it's going to perfectly triangulate, but we just got to make sure that this kind of middle point is exactly where it should be. That can have an extrusion of 0, and I'm going to scale the elements, the edges of these newly created geometries, and as I scale to 0, you can see it perfectly triangulates the fan. How do I get this to triangulate in the correct place? Well, I can just take the position of this point and then make that the center. I'm going to sample the index. Index 0 is fine because we only have a single point anyways. I want its position. I'm going to put this position in the center, and now it is perfectly where it needs to be. Now this, if you're being observant, is going to create kind of extra geometry we don't need. In fact, there should be 1, 2, 3, 4 vertices. Yet we have 6 of them. We have a bunch of stuff that's like overlapping in the middle here. We're going to take that. We're going to merge by distance. Bada bing, bada boom, you're good. And then the rest of this is just kind of iteratively breaking up these triangles, but only if it is inside the circumcircle. Now, in this case, we didn't actually check if it was inside the circumcircle. We knew it because the triangle was so big, but from now on, we have to start checking. Let's take some of our nodes, make them a node group, triangulator, which has a center and it has a input mesh. I'm going to throw this inside of a repeat zone so that we can do this in a loop, and we know our center is already defined by the sample index. Now, there is an issue here because we want to start off with this point and then move on to the next one and next one and next one, and that's going to change over time. Well, because our repeat zone has a iteration that says, are we on the first loop or the second one, the third one, the fourth one? This is exactly going to be the index we preserve. I now plug in our original triangle into this loop. We have a triangle, and then iteration 1, it breaks it up, breaks it up, breaks it up, breaks it up. Now, of course, this isn't correct or perfect because we didn't check the circumcircles, but just follow me here. What is this nastiness? Disgusting. Well, I'm going to take these original points from the triangle, and I'm going to get rid of them, and that is only going to leave the part that we want. Delete geometry. What geometry? The 3 biggest points. Sample the proximity to this triangle. In other words, where is it distance 0? Where are the points overlapping? Where are the ones we want to get rid of? I'm going to check where this distance for points is equal to 0. And for that one, I'm going to delete. That leaves us with this disgusting thing, but it does in fact triangulate our point cloud in a procedural way. So now the name of the game is just checking circumcircles. What a fun way to live.
Oh, sorry guys, I was just feeding my brain with knowledge, which is important to do as a Blender person, and the sponsor of this video, Brilliant, is here to help you with just that. Well, Brilliant is an online platform where they have tons of lessons on like hard skills. We're talking programming, mathematics, there's also interactive puzzles and problems that you solve as you go along, which ensures you know what's going on at all times. This is an effective way to learn because you don't, fall behind. Come a bit closer. Studies have shown that you do this kind of thing every day, it reinforces the learning process and like deeply entrenches in your brain, which is why you can do Brilliant on desktop, sure, but you can also do it on mobile on the go. I'm going to recommend programming, specifically Python modules, because this is the programming language that is compatible with Blender and the one I use to make add-ons. This is a useful thing to know for automating and augmenting Blender. If you want to try this for 30 free full days, there's a link below my head, roughly where the bowl is, along with the QR code you can scan. That will give you this discount, but additionally, you're going to get 20% off the annual premium membership. We love that kind of thing over here. Okay, let's continue.
If I never told you exactly how to get this circumcircle, how do we find this circle such that it has a center, that the radius, the distance to all of these are exactly the same? It can get a bit challenging when our triangle is super skinny. The center is outside of this triangle, so it's not really obvious how to do this. Well, Stephen Wolfram seems to think it's obvious, so we're just going to steal his work. Circumcircle, Wolfram alpha. You basically get an explanation of how to find this exactly, or you look at these formulas over here, which can be a bit intimidating, but all we really care about is how do we find the circumcircle with with a certain center and a certain radius. And to get these values, we just take a bunch of math. I made a random triangle where we can test on. We want to take this and make a circumcircle. So I'm going to join this with a circle. And now we need to find how big is it and where is it centered. So it's telling us this x and y coordinate is dependent on bx and by. Bx and by are these matrices that we get the determinant from. You don't need to know what that means because we have these operations, right? We have matrices and we have the determinant of matrices. So really, at this point, we're just plugging stuff in and hoping for the best. We have x1, y1, x2, y2, etc. These are the coordinates of our 3 points of the triangle. Fine, let's make this big matrix. Combine matrix. Right now, this is the only way to make a matrix, and unfortunately, it is a 4x4 instead of a 3x3, but you know what? I think I can live with that. We're going to have index 0, index 1, and index 2 for our 3 points. I want to extract a vector that tells us where are they. In other words, the position here, here, and here. I'm just going to separate these bad boys out so we have the x and y for all of these that we can control. We're going to kind of suppress the z coordinate. It's not going to get to speak until you do the three-dimensional case. The first kind of column here is just the x values squared. I'm going to take this, I'm going to take it to the power of 2, amazing, to the power of 2, amazing. So we have x1 squared, we have x2 squared, we have x3 squared, but now we have this awkward missing value, because again, it's a 4x4 matrix instead of a 3x3. Blender developers, please. It turns out that we can actually create a 4x4 matrix that ends up having the same determinant just by like extending it in this weird way. 4x4 matrix that has A, B, C, D, E. We go to F, we go J. That is a disgusting G. H, I. How do we take this 3x3 and extend it to be a 4x4 such that it has the same determinant? I have a 3x3 matrix, but I can only use 4x4. How can I extend same determinant? What's it gonna say? ChatGPT wisdom. I think it's gonna say add zeros and ones. So, okay, we add zeros on the right, we add them below, and then we add a 1 on the bottom right corner. Fine. Well, because we are filling in the first column, there should be a 0 here, so we're gonna keep the 0. And I think I missed something. This first column is the addition of the powers. X and y, x squared, y squared, add them together, and then replace this value over here, and then we're just gonna do that again and again. And I know, folks, we're going in the weeds here. Is this fun 3D animation, or is it, meticulous, boring math? I ask you, what is the difference? We're going to get back to the good stuff in a second. We are in business. The next column here is just the y coordinates, plain and simple. So y coordinate 1, y coordinate 2, y coordinate 3. This column over here is again going to end with a 0. The third column is just a bunch of 1s. That again is going to end with a 0. Easy enough. So 1, 1, 1, 0. And then finally, this fourth column that doesn't really exist here, it's going to be a bunch of zeros, but this time it's going to end in a 1. So this is our first matrix. To get the determinant negative of it, we take this matrix, we get the determinant. That's just going to be a number. You could almost think of it as area, or you could not think about it. That's what I prefer. And we're going to take that, we're going to multiply it by -1, and just like that, we have bx. That is part of what we need, but now we need by. You're going to notice by is almost the same. In fact, the only difference is column 2. Instead of having y's, it has x's. X coordinates for the second column here, we again have 1, 1, 1, 0, and then 0, 0, 0, 1. So really, most of the work here was just making this first matrix. And for this one, we need the determinant, but not the negative determinant. Final thing is it says we need this A. What is A? Well, let's find out. Wolfram says it's this matrix. We have x's, we have y's, and then we have 1s. Okay, super easy. We have x, we have y. By the way, there are other ways to get the circumcircle, but it's not going to be as fast as this formula that some genius figured out for us. So we're just going to stick with it. Rest of these are the same, and we need the determinant for this. Okay, let's pack this nonsense away. Control H. I never want to see it again. Bx, by, and this bad boy, I'm going to call it A. And at this point, allegedly, the coordinates are this simple division thing. So for the x, we take bx, we multiply it by -1. Interesting. In that case, we don't need to multiply by -1 twice. And then I'm just going to take it and divide it by 2 times A. Here's A multiplied by 2. And here's our first coordinate. Amazing. Now we take by. We have to multiply by -1, but this time it doesn't undo itself. And then I'm going to divide by 2a. And allegedly, this is our x and y coordinates. Now, boys, I know none of us know what's going on anymore, and that's fine. All of this nonsense, all of it, is just to get the circumcircle, or really the center of it, for a given triangle with index 0, 1, and 2. We now have a circle that at least we know where it's supposed to be centered. So I'm going to transform geometry such that this is the translation. It doesn't doesn't like that because that is a field value. We can just sample index. Doesn't matter. I'm going to take my triangle. I'm going to sample the index, and I'm going to say, tell me what the center was at index 0, 1, or 2. It's the same everywhere. And I'm going to plug that in right here. And now it shifted over our circle. Now, is this correct? Time will tell. But if we increase the radius, you can see magic number. Okay, there is some radius that works. Well, because we know the center of this now and the radius, the distance to all of these should be the same, let's just calculate the distance between this one and index 0. Sample index again. This time, instead of our special coordinate, I'm just going to take the position, and then I'm going to calculate the distance between the twain and connect that to scale. And boys, we are in business. Because now, whatever transformation we do, whether that be a movement, rotation? Not rotation, we're in 2D. Or a scaling, it's going to find the perfect circumcircle. See how it's almost correct, but just a bit off. It's just a bit off. That tells me that somewhere I didn't multiply or something. Be right back. Okay, I figured it out. You know how we're supposed to do powers of 2? I don't know why I connected this one over here. So this is a power of 2. I add, and look at that. That's what we call a quick fix. So now, whatever we do, whatever transformation, yeah, we love it. And notice that these skinny triangles make giant circumcircles, and that's why it's an issue. We don't need them. Okay, cool. Basically, all this nonsense just says we take a triangle, which I can give it some geometry by saying make a n-gon, and we put a circle on it. We're going to take this, and we're going to loop it for every face. You don't need to actually draw the circle. We just need to know what it should be. In other words, take all of this, and make it a node group. I want to output the coordinates, and I want to output the distance, which is the radius. Coordinates, radius, circumcircle. Well, now, instead of blindly iterating, we can make sure we're deleting the right faces and triangulating those. So before we put something in our triangulator, we got to make sure that it is the right thing. I am going to separate them to only bring in the affected faces. It might just be one triangle, it might be two triangles, but these are the ones I care about. And remember, if I have a point here, we need to check, is it inside the circumcircle? It's as simple as, here's the center of our circumcircle, we're going to check if the distance between these is smaller than the radius. If that's the case, it has to be inside. It hasn't reached far enough to get out of the circle. I'm going to take the distance between our current point and our coordinate, and I'm going to check, is that indeed less than the radius? In other words, this outputs, is it a degenerate, naughty, bad triangle? I'm going to separate faces by this, which will now tell us which triangles are the offenders. And we got to make sure that we're piping in our input into the circumcircle. It's almost going to work, not quite. You see, if I get rid of these like triangles, it's still a mess, right? This is not a good triangulation. And that is because, yes, we are saying which triangles are degenerate, but there still might be some issues. Like, let's say that we have two degenerate triangles. In this case, we're going to get rid of this edge that connects them. That is going to make this big polygon over here. And then this, wherever the point is, let's say it's over here, this is what we're going to triangulate. Now, what's the issue? What we've done is we've indeed said this triangle is an issue. We've said this triangle is an issue, but we never got rid of this edge. And I'm saying it like it's profound. How do we get rid of that edge? To isolate this edge, but not all of the others, there's one thing it has in common, always. This edge is the one that's touching the faces, both of them. Here, we've separated the faces. I'm then going to separate the edges, such that we get rid of the ones that are bad. So we are going to take the edge neighbors. This is going to tell us how many faces is each edge touching. Where is it equal to 1? In other words, it has to be in the perimeter. Yeah, and I'm going to keep those. Now, you can see that this kind of like almost works, but it like deletes geometry where it shouldn't. And that's because of something a bit nuanced. It took me a bit to debug. We're assuming that this circumcircle thing is calculated and then sent in a correct way. That is not necessarily the case because we need this for every single face. And right now it's assuming that it has a single face as an input. We're saying take index 0, 1, or 2 as if there's only 3 vertices. But if there are like 2 joining faces that are an issue, well, there's 2 faces and more than 3 vertices to deal with. Worry not. All we need to do is we need to take this and say like do it for every face. This is where the for each zone, this is kind of new to 4.34 something. This is where this comes in. It lets you do an operation, but for every face. I'm going to take this, I'm going to connect it over here, and I'm going to say for each face, we're going to do this operation. Let's make this bigger. I'm going to take the face that we're currently working on. I'm going to connect it over here. Then instead of like piping these out directly, I'm going to make sure we store them on every single face. I'm going to keep the geometry and I'm going to store on the faces the center and the distance. So instead of just bringing it out here, it's now in the geometry. And once I do that, I just need to make sure these are swapped so that we are using the center and we are using the distance that was stored here. We've separated out the faces that have the circumcircle degeneracy and have that issue. So let's say we have a K case like this that has these degenerate faces, we said we had to get rid of these edges that kind of combine them. I want to get rid of any edge such that the face count is equal to 2. I think it was set to 1, but it's equal to 2. And then just to make sure that there are no like n-gons or faces left, I'm going to delete faces for every single face. And then finally, because we did separate out our triangles in this like for each zone, it separates them, stores them, and then recombines them. I got to make sure to merge by distance. And I think that did it. I think that gosh dang did it. Let's see. Delete geometry. Look at that. So this isn't just a triangulation. It's the one that like minimizes skinny triangles. Although it is missing a point here. Why did I add one here? Get rid of that. And this should be fairly fast to calculate. If I add more points, I got to make sure that it satisfies that by adding more iterations, or I can just look at how many points we have. Domain size, how many points are there, and make that the iteration. Now, I think it's very possible I made a mistake at any part here, but I think I got the essence of it. Now, you might ask yourself, how can I make this faster? One thing we can do is right now we're calculating the circumcircle for every single face, every single time. Now, that doesn't make sense because we usually only need to deal with some of them. It probably makes sense to store this data and then we say skip if it's not something that needs to be updated. That way, we're not calculating over and over and over again. And a bit of a fun fact, Voronoi, like that fragmentation pattern, I think it's called the dual of this graph. What that means is if I literally add a node called dual mesh, you can see it makes this Voronoi thing. If I keep boundaries, it will do that. This is how you fragment something, and it should be correct or nearly correct. These are dual ideas. What that means is for every single face like this one, I can replace it with a point. Same for this face. And if faces are touching, you connect them with an edge. So it's just kind of flipping the graph in some sense. And then as a final thing, you're going to see if I go to solid view, yes, it has the faces, but the normals are jank. I'm going to enable face orientation. Some of them are going to be pointed up and some of them are going to be pointed down. That makes sense. We didn't really specify the order in which to make faces. So I'm going to flip faces, which will invert this, but only if they're facing down. To check if it's facing down, I can take the dot product and see if it aligns with 0, 0, -1. This is a indicator. It will tell us, does this face down? Is it aligned with the 0, 0, -1? I connect this here, and now we have a nice continuous normals. Now, this whole thing gets way more complicated. It gets way more complicated for 3 dimensions, yet the ideas are still kind of the same. Your points need to satisfy a circumsphere, which just has bigger matrices and determinants, and instead of closing in a triangle, you have to close in like a convex solid. I don't even know. You gotta know when to end it, so hopefully hopefully you learned something. This is more of a conceptual thing, but you take it to the 3rd dimension and it becomes quite useful. Like in photogrammetry, you can't really skin or surface reconstruct a point cloud without these ideas. Again, in Genie, I made a 3-dimensional version of this using a bit of a different idea. I'm calling it concave hull because it can actually match the shape of the thing even if there's concavities. Okay, I've gone on for too long, and quite frankly, goodbye.